Oh yeah, here we go. We're now going to put our logistic growth skills to the test. Let's do it. The logistic equation given below models a population. Use the equations to find K, find the carrying capacity, and do a whole bunch of other stuff. Let's just go piece by piece, all right? So number one, we're given that P of T equals 2,000 over 1 plus 19e to the minus 0.1 t. What I like to do with this is, I like to look at this and say, okay, this is the same as P of T is equal to, and I like to write out my template, L, the carrying capacity, all over 1 plus CE to the minus KT. All right, important to note that C is not necessarily your initial population. So it asks us to just find K, right, that proportionality constant. Well, the K value's in this spot right here, so it's 0.1. It's not negative. It's positive 0.1 because it's minus KT. So you could write that for part A, minus K equals minus 0.1, and therefore K equals 0.1. That's it. That's A. Let's keep going. All right, find the carrying capacity. Well, the carrying capacity is L, right? It's that limiting amount. So L, what's in the place of that here in your logistic growth population function? 2,000. That's it. So L equals 2,000. And we're not told if it's people, aardvarks. We're not told what it is. All right, we'll go with aardvarks. It's fun. Find the initial population. Well, it's not just C, right? So we don't just say, well, the initial population is C. No, not quite. The initial population happens when T equals 0. So let's plug that in. T equals 0 into here, right there. And we're going to get 2,000 all over 1 plus 19e to the negative 0.1 times 0. Not bad. So now from here, that's going to be equal to 2,000, and I'm going to write this real properly, P of 0, right? We're plugging 0 into the population function. So it's 2,000 all over 1 plus e to the 0 is 1. So 1 times 19 is 19. So it's going to be 2,000 all over 20, which is equal to, last I checked, 100. So your initial population is 100 of whatever it is. Then it says determine at what time t the population will be increasing the quickest. Okay, so I'm going to go to the next page for this so we have a little bit more room. So we're going to need a little bit more room for it. So at what time t will the population be increasing the quickest? Now I said in the first part of this lesson, in our first video, the population is increasing the quickest when we're at half the carrying capacity. So if you needed to justify your answer, you could say the population is increasing quickest when P of t equals half of the carrying capacity. And half of the carrying capacity is equal to 1,000. That's it. You don't even have to justify it further than that. That's enough. But here it didn't say what's the population when it's increasing the quickest. We want to know what the time is. So we take that 1,000, and that is the population value. We set it equal to 2,000 all over 1 plus 19 e to the minus 0.1 t. All right. So what we do here is we got to solve this out. The best way to do that is multiply both sides by this denominator. So we get 1,000 times 1 plus 19e to the minus 0.1 t is equal to 2,000. Just multiply both sides by this denominator. We're going to divide both sides by 1,000. We get 1 plus 19e to the minus 0.1 t is equal to 2. 2,000 divided by 1,000 is 2. Subtract 1. So you get 19e to the minus 0.1 t is equal to 1. Interesting stuff's going to happen here. We're going to divide both sides by 19. I don't know what this number is going to be, but it's not going to be pretty, I can tell you that much. E to the negative 0.1 t equals 1/19. We're going to take the ln of both sides because, well, we got to get rid of that e. So take the ln of both sides, and you end up with e to the negative 0.1 t. The ln of e completely inverts itself. Is equal to ln of 1/19. And I should erase this part right here. We now have negative 0.1 t. Right, because that e is now gone. And so that then gives us, I'll put that here, ln of 1/19 divided by negative 0.1. So ln of 1/19 divided by negative 0.1. That'll be our time, but what is that time? Well, I'll be back to you in a jiffy with the calculator's decimal for that. And with a little bit of shoddy video editing, here we go. We've got a final answer, 29.444 years, days, whatever the units of measurement are. All right, that's part D right there, rocking it. The important part there is that at half the carrying capacity of any logistic growth situation, we will have the fastest rate of growth. It's cool. And I went over the why behind that, the logistics of that, little pun, in the last video. Finally, write a logistic differential equation with solution P of t. Now this equation you also have to memorize. Now we're using P, so I guess I'll do, instead of dy, I'll do dp dt. So we'll do dp dt, the differential equation is the rate of growth. dp dt is equal to k times p, or y if you're using y, 1 minus p over L. Okay, now, you got to memorize that, but I went over the why behind it in the first video. I hope you check that out because it'll help you to memorize it. You also have to memorize the general form of this as well, and you'll be in good shape. You'll never have to derive them, not unless you have a crazy teacher. Now, let's take a look at this right here. We're going to use that and the information we have. So dp dt is equal to, now what's the k value? It's 0.1. We actually found that in part A in the previous slide there. So 0.1 times p times quantity 1 minus p is unknown, right? It's just left open. And L we know is 2,000. There we have it. There's your differential equation. Not so bad to do. All right, made quick work of that one. I'll see you in the next video. More logistic growth. Until then, peace.